Okay. Good morning, everyone. In the last session, we started with unit number 3, that is second law of thermodynamics. And in the beginning itself, we discussed the limitations of first law. As we were about to begin the unit number 2, that is second law of thermodynamics, it is but obvious that we should know what is the need of studying the second law of thermodynamics. So we started with the limitations of first law of thermodynamics. So can you just enlist those limitations that we discussed in the last session? Ankit, tell me one of the limitation of first law. We discussed 3-4 limitations. You just need to tell me one.
So we did not know the internal energy of the exact number of internal energy.
That is not the limitation of first law. Where did you get this one? That is not limitation of first law. Anybody else? Rushikesh, tell me one of the limitation of first law. Anyone? Ankit, you want to say something? Rishikesh DK, you there?
Hello?
Limitation of
Hello?
first law. Rishikesh, can you hear me? You need to tell me one of the limitation of first law of thermodynamics.
Sir,
Yes, Ankit.
it does not tell the direction of the
Process.
flow of internal energy.
It does not talk about the direction of the process. That is one of the limitation. Okay. 2 more are there. Afroj, can you tell me another one limitation? Adinath.
Yes, sir.
Adinath? Yes.
Yes, sir.
Tell me second limitation of first law. First one is it does not talk about the direction of the process. What is second one? Adinath, do you know the answer? If you don't know, mute yourself. I'll ask to somebody else. Narayan.
No, sir.
Okay, no problem. Narayan. Narayan
Yes, sir.
Borani.
Yes, sir.
Tell me the second limitation of first law.
No, sir.
No, sir, there isn't any limitation, right? The first law is far superior, that it doesn't have any limitation. Very good. अभ्यास करा रे असं करून नाही चालणार. Okay, mute yourself. So the first law of thermodynamics, the statement is energy cannot be created nor destroyed. It can be converted from one form of energy to the another one, right? That is the first law of thermodynamics. It is also called as the law of conservation of energy because it says that we cannot create, we cannot destroy. So it simply says that energy is going to be conserved. So it is also called as law of conservation of energy. Additionally, the first law of thermodynamics is also a statement that is called as quantitative in nature. Quantitative in the nature, in the sense, it does not talk about quality of the energy, it just highlights the quantity of the energy. In that sense, it says that one form of energy can be converted into another form. Now, what is meant by quality? Quality in the sense, there are various forms of energy. If you convert one form of energy into another, you might have some different conversion rate, whereas if you convert that energy into some other form, then you might get some different conversion rate. So the variation in that conversion rate is nothing but the quality of that particular energy. If energy has better quality, you can have more conversion rate or you will have more efficiency. But if you are dealing with low grade energy or having lower quality energy, then that conversion rate will be less. So efficiency will be less. Like for example, as first law talks about the conversion of heat into work and work into heat, when you convert work into heat, you can have 100% conversion, whereas when you convert heat into work, that efficiency falls below 50%, right? Because heat is low grade energy, low quality energy, whereas work is high grade energy or high quality energy. Okay, so the limitation of first law is, it says that energy can be converted from one form to the another, but it never talks about amount in which energy can be converted from one form to the another. Okay, and that is related to the quality of energy. That is the first limitation. Second one, also it does not talk about condition under which that conversion is possible. It says that heat can be converted into work or work can be converted into heat, or one form of energy can be converted into another one, but that conversion will be possible under specific conditions. And first law never talks about those specific conditions, right? That is the another limitation. Then it never talks about the direction of the process. Means if I keep a hot cup of tea in an open atmosphere, that is at lower temperature as compared to coffee in the cup, we know that the coffee is going to get colder by transferring heat from to coffee to the atmosphere. But even if I say that instead of transferring heat from coffee to atmosphere, heat is being absorbed from the cold atmosphere and coffee is getting further hot. If I say that, even then the first law is not being violated. So that is the limitation of first law. Okay, so these are the limitations associated with the first law of thermodynamics, and because of those limitations, or as those limitations are there, the second law need to be studied. Okay, and the limitations associated with the first law, all of the limitations has been overcome by the second law. So the uses of second laws are like, now we can talk about direction of the process. Now we know various qualities of various energies. Also, we know the theoretical limits while having that conversion, right? So these are the uses of second law, and those are the actually remedies of the limitations of first law. That's why we need to study the second law of thermodynamics. Then we talked about the thermal energy reservoir. Now, thermal energy reservoir in the sense, a body that has a large heat storing capacity. If that body can store a large amount of heat, and if you extract heat from that body, or if you add heat into that body, its temperature remains constant or its temperature remains unaltered. Means if you subtract heat from that body or if you add heat to that body, its temperature is going to remain constant, and then we can call that body as a thermal reservoir. If you are taking heat from that thermal reservoir, it will become source. If you are rejecting heat to that thermal reservoir, it will become sink. So both are the thermal reservoirs. One is going to provide the heat, another one is going to accept the heat. So the one that provides the heat called as source, and other one is called as sink. So that is basically a thermal energy reservoir. Then we talked about heat engine. Heat engine is basically a device that converts heat into work. We provide heat as an input and we get work as an output. If you look at its diagram over here, this is our heat engine that accepts heat from a high temperature reservoir that we can call a source. The amount of heat accepted is QH. H stands for high. TH is T higher, and it is accepting heat from high temperature reservoir. This is Q higher. It produces net work output W net out, and it rejects some heat QL to another reservoir which is at lower temperature compared to this reservoir, and this one is low temperature reservoir. Temperature is T lower, and the amount of heat rejected by heat engine to low temperature reservoir is QL. Now in this conversion, engine accepts heat QH, produces W net out work output, and rejects some amount of heat to the low temperature sink, that is QL. Now if I write the thermal efficiency, or it is nothing but a performance measure of the device heat engine, then the relation is thermal efficiency is equal to net work output to the net heat input, or in other words, this is output and this is input. Output to the input. In case of heat engine, output is net work output, whereas input is QH, that is net heat supplied. So N thermal is equal to W net out by Q in. I have written Q in over here. Why Q in? This QH is entering the heat engine. So this QH also can be called as Q in, whereas this QL is going out of the heat engine. This can be also called as Q out. Okay, so don't get confused in those two terms. QH is nothing but Q in. Also this QH or Q in can be called as Q1 also. So while solving numericals, there may be Q1 and Q2 also. So don't get confused in that also. So N thermal is equal to W net out by Q in. Now this W net out is nothing but, if I write the relation between W net, QH and QL. In case of heat engine, there are three interactions between system and surrounding. Except heat engine is our system, and anything beyond heat engine is our surrounding. So it is taking heat QH, it is rejecting heat QL, it is producing W net, uh, W net out work output. Okay, so if I write relation between those two, this is entering the system, this is leaving the system, and this is also going out of the system. So W net out is going to be the difference between heat entering the system and heat leaving the system. So W net out is equal to QH minus QL. This is entering the system and QL is leaving the system, because there are only three interactions. This is going out, this is going in, this is also going out. So the difference between this heat entering heat and heat leaving is nothing but the work produced. So W net out is equal to Q in minus Q out, or QH minus QL. And if I replace this numerator W net out by Q in minus Q out, I will get this next relation. Sorry. N thermal is equal to 1 minus Q out by Q in, because if I replace this W net out by Q in minus Q out, Q in by Q in, I will get 1, and minus Q out by Q in as it is. So this is the relation for thermal efficiency in case of heat engine. We solved this numerical also. Okay, then we talked about whether the efficiency can be increased by reducing this QL to 0, because we know that the numerator is going to be difference between Q in and Q out. If I reduce the value of Q out, the numerator will increase, and that will lead to increase in the efficiency. So if I can reduce this Q out to 0, I can make efficiency of that engine as a 100%. So we discussed that one, whether we can achieve that 100% efficiency, and the answer is no, because to execute the cycle, it is supposed to reject some heat to the low temperature sink, and because of that one, heat engine can never have efficiency that is equal to 100%. That we discussed over here. Then we discussed the one of the statement of second law of thermodynamics. This statement is Kelvin-Planck statement. This one is related to heat engine. So it is going to be related to conversion of heat into work. Heat engine always converts heat into work. So Kelvin-Planck statement deals with heat engine, or Kelvin-Planck statement deals with the conversion of heat into work. So what statement is? It is impossible for a device that operates on a cycle to receive heat from single reservoir. If you look at the heat engine over here, it is interacting with single reservoir. It is accepting heat from high temperature reservoir QH and produce net amount of work output, and it is converting that all the heat accepted into work. If you look over here, I have written QL is equal to 0. It means that this heat engine taking heat from single reservoir and converting all that heat into useful work. So because of that one, I can say this engine has got 100% efficiency, right? But it is impossible, because we know that this QL cannot be 0. This is always going to be greater than 0, because it needs to complete the cycle. So no heat engine can have thermal efficiency of 100%, or as for power plant to operate, the working fluid must exchange heat with the environment as well as furnace. Now this one is heat engine. If I consider furnace, the reservoir from where it is going to accept heat will be a furnace, whereas the reservoir it will reject the heat will be environment or atmosphere. So that power plant has to exchange heat with those two, source as well as sink. Similarly, heat engine need to exchange heat with the two reservoirs, source as well as sink also. Okay, we discussed this one also in the last session. Now we were about to begin with the refrigerator. Now all of you must have refrigerator in your house. Few may be there, those who don't have that refrigerator, but need not to worry. So what is the working principle of refrigerator? How does it works? So let's begin with the flow diagram or sketch of the working cycle of refrigerator. Now, a refrigerator has got four major parts. First one is condenser, second one is compressor, third one is evaporator, and fourth one is expansion, or in some books you might find throttling wall over there, throttling wall or expansion wall, or even capillary tube. All these are the having same function, so don't worry about that one. So the four major parts are condenser, compressor, evaporator, and expansion valve. Now, how that process exactly takes place? To understand that working in a better way, I have a small video over here, so that I'm going to play. Let me exit the full screen. Okay, so let me discuss this in details so that you can have better understanding. What time is left out to end the meeting? It is not showing remaining time. Okay, let's continue. Let's see what happens. Okay, so the major parts of the refrigerators are, first one is condenser. So what is the function of condenser? Actually, this condenser and this evaporator both are the kind of heat exchangers, right? While looking at the steady flow energy equation in first law of thermodynamics, that is second unit, we have discussed about those two devices, right? So those two devices are the integral parts of any refrigeration system. For air conditioning system also they are going to be there. So the condenser and evaporator, let's talk about those two first. So this evaporator and condenser are the heat exchangers or the tubes through which the working fluid is going to flow, and heat is going to be exchanged between tubes and the surrounding atmosphere. So the tubes that are inside the refrigerator, means you have got that refrigerator box, and the tubes inside the refrigerator that is going to extract heat from the food. You are going to keep some food in that refrigerator, and that is expected to be cooled. So heat is supposed to be extracted from that food, and that will be achieved through this heat exchanger called as evaporator. So evaporator tubes are going to be inside the refrigerator. The second heat exchanger is this condenser. These are the tubes that you see on the back side of the refrigerator, that is going to be exposed to the atmosphere, because those are expected to transfer heat to the atmosphere. So that is another heat exchanger. So the function of condenser is transfer heat from working substance to the atmosphere. So it is going to lose the heat to the open atmosphere, whereas evaporator is going to accept heat from the food that has been kept in the refrigerator. Now, in condenser, when it rejects the heat to the atmosphere, then it enters the expansion valve. We are going to consider that cycle has started from the condenser. The function of condenser is to reject heat to the atmosphere. So when it rejects heat, its temperature will drop by some value. You can see over here, here the temperature is 60 degree, and when it passes through the condenser, its temperature has got reduced to 30 degrees Celsius. Now in expansion valve, this is expansion valve or capillary tube or throttling valve also. Here the velocity will be increased, pressure will be reduced, and because of that one, a temperature will dropped. Velocity increases, sorry, pressure reduces, and because of reduction in pressure, its temperature also reduces, and that temperature becomes minus 25 degrees Celsius. So here it rejects heat to the atmosphere, its temperature drops by some value, pressure also gets dropped by the some, pressure drops over here, like over here from 800 kilopascal to it becomes 120 kilopascal. Here there will be only reduction in temperature as heat is transferred to the atmosphere. When it passes through expansion wall, its pressure reduces, its temperature further reduces, and then fluid enters the evaporator, that is the tubes inside the refrigerator, where the tubes are expected to absorb heat from the refrigerator. As its temperature has got fallen to a lowest value like minus 25 degrees Celsius, it can easily absorb heat from the food, because food is not going to be that cold. So it will absorb heat from the food, and its temperature will increase slightly. There will be very small amount of increase in its temperature, but uh, here if it is liquid, here it will be vapor, because in evaporator its boiling point will be reduced, and because of that one, even at this low temperature, by absorbing heat from the food, the refrigerant gets converted into vapor, and its temperature remains almost constant, minus 25 to minus 20. So there is only difference of 5 degrees Celsius, and its phase will change from liquid to vapor. Then it is supplied to a compressor. Now in compressor, its pressure will be increased. Because of increase in pressure, its temperature will increase, and then it is supplied to a condenser. Here you can see that pressure from 120 kilopascal has become 800 kilopascal. Temperature from minus 20 has become 60 degrees Celsius. And when that high pressure, high temperature vapor comes in condenser, it will reject heat to the atmosphere, and that way cycle will continue. And through this continuous cycle, it will continuously absorb heat from the refrigerator and continuously reject heat to the atmosphere. So that way it maintains the cold temperature in the refrigerator. So that is going to be working principle of the refrigerator. Now, if you have any query, you can unmute and ask, or even you can post it in a chat window. I'll wait for a while. I'm
Sir,
expecting.
evaporator, sir. Point.
Yes, Pratik, can you repeat the question?
Sir, at minus 20 degrees Celsius, it is in vapor form or liquid?
1 second, let me clear all the markings that I have made over here. Yes, Pratik, repeat the question, please.
Sir, that at minus 20 degrees Celsius,
Here.
yeah,
Hmm.
the heat is absorbed from food. It is in vapor form or
It will be in
liquid?
vapor form, semi vapor form. When liquid is over here, it will be in liquid form. Temperature is minus 20. So when it comes in evaporator, it accepts heat from the food, and its temperature almost remains constant, but it gets converted into vapor. But there will not be a conversion of 100% liquid into 100% vapor. That is not the case. Some liquid will get converted into vapor, and when it enters over here, it will be mixture of liquid plus vapor, and that liquid plus vapor will be then fed to a compressor for increasing its pressure and temperature both. Is that clear?
Yes, sir.
Okay, any other query? Actually, in the video, somewhere I heard that in compressor, because of increase in pressure, the temperature also increases, right? And he mentioned that that is unavoidable, but actually that is required one. Why this increase in temperature is required is that, now see, when working fluid enters the evaporator, it is expected to have temperature lower than the food. Then only it is going to accept the heat from the food, right? And that we can achieve through this condensation and expansion wall, because some temperature drop will be over here and further temperature drop will be over here after the expansion wall, so that we can achieve temperature, or we can reduce the temperature of working fluid lower than the temperature of the food. Similarly, in condenser, if you want to transfer heat from working fluid to open atmosphere, then the temperature of working fluid must be greater than temperature of atmosphere. Then only heat is going to be transferred from working fluid to the atmosphere. And for that one, when fluid enters, when this liquid and vapor mixtures enters the compressor, its pressure and temperature is increased, and that temperature is increased above the temperature of atmosphere. And when that working fluid's temperature has got increased beyond the atmospheric temperature in condenser, it can easily transfer heat to the atmosphere. Okay, is that clear? Any doubt, any query? Now, based on the
Compressors working.
uh, everything is fine. Pratik?
So repeat the working of compressor.
Okay, I'll repeat whole cycle again. Erase all ink. Okay. So the let's consider working starts from condenser. Condenser is a kind of heat exchanger. It is going to reject heat to the atmosphere. Actually, throughout the cycle, there is certain working fluid that is going to flow. There are various working fluids that are used in the refrigeration systems. So in condenser, the working fluid reject heat to the atmosphere and its temperature drops from 60 degrees Celsius, it becomes 30 degrees Celsius. Now, this low temperature liquid, when it passes through this expansion wall, its pressure decreases and its temperature also decreases. So my 30 degrees Celsius becomes minus 25, 800 kilopascal becomes 120 kilopascal. So as its pressure and temperature has got reduced, when it comes in the second heat exchanger, that is evaporator or tubing inside the refrigerator, as the temperature of working fluid is minus 25, that is going to be less than the food stored in the refrigerator box, it accepts heat from the refrigerator or from the food and it gets vaporized. Some part of liquid gets vaporized, its pressure remains same, temperature increases slightly, and there will be change in phase. If it is liquid over here, it will become vapor over here, and then that liquid plus vapor mixture will be supplied to a compressor. Now in compression process itself or during the compression, it is obvious that as it is compressor, it is expected to increase the pressure. But while discussing steady flow energy equation for the compressor, we said that when you try to increase the pressure, its temperature also increases. And same thing happens over here also. So after compression process, its temperature becomes minus 20 to plus 60 degrees Celsius, and pressure also increases from 120 kilopascal to 800 kilopascal. And this high temperature, high pressure fluid, when it comes in contact with the condenser, it will again reject heat to the atmosphere and it will begin for the next cycle. So here it is expected to be a high temperature, high pressure liquid, and to achieve that state the compressor is used, because compressor increases the pressure as well as increases the temperature, and that is the requirement of transfer of heat in condenser from system to the surrounding. So that is the basic application of the compressor. Now is that clear, Pratik, or still there is any doubt?
No, sir.
Okay. And now as we have seen working cycle for the refrigerator, now this cycle is going to be there for, let it be air conditioning system, let it be ice plant, anywhere wherever you are transferring heat, or whenever you are maintaining temperature of some system below atmospheric temperature by transferring heat from that system to the surrounding, this cycle is going to be there. So let it be air conditioning system, refrigeration system, ice plants, or even in foreign countries, when the temperature falls below 0 degrees Celsius, instead of cooling the house, they will use heating the house, right? So in case of those heating systems also, similar cycle is going to be there. Just the difference is going to be, instead of evaporator fitting inside the system, evaporator will be outside the system and condenser will be inside the system. So instead of making the system cooler, it will start making the system hotter, or it will start increasing the temperature of the system. But the working cycle is going to remain same. All parts are going to be there: condenser, expansion valve, evaporator, and compressor. Okay. Now let's discuss the uh, performance measures associated with the refrigeration system.
Have you ever wondered?
Now,
Have
this is our refrigerator that is going to transfer heat from low temperature body, cold refrigerator space. This is our fridge, or the space where the food is being stored. It accepts heat from that cold refrigerator space, which is at temperature TL, transfers heat to a warm environment having temperature TH, and here they have mentioned that TH is higher than TL. So we know that this is atmospheric temperature and this is refrigerator temperature, the temperature inside the box. So this temperature is always going to be less than atmospheric temperature, or atmospheric temperature is going to be higher than this temperature. So TH is greater than TL. So the refrigerator is there that is accepting heat from the refrigerator space, transferring heat to the open atmosphere, and for that one it is using the external work W net in, and that work will be provided by compressor. So this is working cycle. When you are discussing the refrigeration system, you are supposed to draw this sketch as well as draw this sketch.
Have you ever
Both these sketches are expected to be drawn. So the interactions are W net in, work is entering the system, work is consumed by the system. We know that compressor is a work consuming device. So it is going to accept the work and work is going to be negative. It is going to accept heat from low temperature body and it is going to reject heat to a high temperature body. So the interactions are W net in, QL and QH. Now W net entering the system, QL entering the system and QH is going out of the system. So I can easily write a relation that QH is equal to W plus QL. Is that fine? Because this is entering the system, this is entering the system and this is going out of the system. So this must be equivalent to this W net plus QL, right? So W is equal to Q higher minus Q lower. Okay, this relation we got over here. Okay, now just like heat engine, we talked about the term N thermal, that is thermal efficiency. In case of refrigerator or heat pump, that thermal efficiency will be replaced by coefficient of performance called as COP. So when you are talking about refrigerator or heat pump, you are not supposed to use the term N thermal. N thermal is related to heat engine only. If you are talking about refrigerator or heat pump, you are supposed to use the term coefficient of performance. Relation is going to be same. COP, coefficient of performance of refrigerator, COP-R is equal to, for heat engine efficiency was output by input, right? Similarly, COP of refrigerator will be desired output by required input. Ultimately, it is output by input, but desired output by required input. Why this word desired is there, you will be able to get why desired word is there only after studying the heat pump. So at the moment, just remember that COP of refrigerator will be equal to desired output by required input. So in case of refrigerator, what is desired output? This QH is desired or this QL is desired? What do we expect while transferring heat from that refrigerator to the atmosphere? By maintaining temperature of atmosphere or by maintaining temperature of the refrigerator?
Refrigerator.
Exactly, the maintaining of temperature of refrigerator is our focus, right? So this QL is now desired effect, right? So COP of refrigerator is equal to QL, that is the output, and input is going to be W net in, and that is QH minus QL that we have derived over here, right? So COP of refrigerator is equal to QL, that is desired output, divided by QH minus QL, that is required input. And if you divide numerator separately, you will get this relation 1 by QH by QL minus 1. So that is the relation for COP of refrigerator. Now additionally, there will be one relation. Now this is, let me clear everything again. Okay. So this is QH interaction with the source having temperature TH. This is QL interaction with the source, not source. I will use word reservoir, because source is somewhere where heat is being accepted, and sink is the where heat is being rejected. So QH is the temperature, sorry, heat interaction with the reservoir having temperature TH. QL is the heat interaction with the reservoir having temperature TL, and this QH will be always proportional to TH. Similarly, this QL will be proportional to TL. So this QL and QH can be replaced by TH and TL. So COP of refrigerator can also be T lower by T higher minus T lower. That could be a alternative relation, when instead of heat transfer, if they have given temperature and ask you to calculate COP, then you are supposed to use this relation, because QL is equivalent to TL. So numerator will be TL, and QH minus QL will become TH minus TL. Okay, now there is one question: can value of COP be greater than unity? If you look at this relation, or if you look at this relation, and remember that QH is greater than QL, or TH is greater than TL, can you answer this question? Take a few seconds and tell me if that is possible or impossible. Pratik, any guess?
Yes, sir.
Is that possible or not possible?
No, sir. Greater than नाही होणार.
नाही होणार, बरोबर, कारण इथं आपण इझिली पाहू शकतो QL जो आहे हा स्मॉलर आहे, QH मायनस QL दोन्हीतला मी जो डिफरन्स घेईल, as QH is greater than QL, the denominator is always going to be greater than 1, so this value will be always less than 1. So COP of refrigerator can never be greater than unity. Okay. Okay, so now next device is a heat pump. Now you will get the importance of this word desired output. Why instead of output and input, I have written desired output by required input. Now, as I said, the refrigerator and heat pump are going to work on the same cycle. Nothing is going to be changed. So what changes are there that makes heat pump as a different device? The changes are, let me explain over here only. Now this is our body in the sense its temperature or maintaining temperature of this one is the our area of interest. The temperature of this one is doesn't matter to us, right? The maintaining of temperature of cold refrigerator space is important. So the taking the amount of heat taken from here is the desired effect, or maintained temperature TL is the desired effect, right? Now this will be replaced by atmosphere, and why this toolbar is coming in between? Okay, and this will be replaced by our house. You got the difference? Now the body has been replaced by atmosphere and atmosphere has been replaced by body. I am considering house as a body whose temperature is to be maintained. So when you replace that atmosphere and body with each other, you will get refrigerator and heat pump. Now I will discuss the heat pump. Now this is heat pump. It is going to accept heat from the cold environment. See, now it has become a environment. In case of refrigerator, that was our body. So from cold environment, that is at a temperature of TL, it is accepting heat QL, it is consuming work W net for running that compressor and all, and it is transferring heat QH to a house which is to be maintained at temperature TH, and again this TH is greater than TL. So it is going to transfer heat from low temperature body to high temperature body, but now the high temperature body is our desired body or desired effect, whereas low temperature body is now atmosphere. So now if I write the relation for COP of heat pump, the relation is desired output by required input, and in case of heat pump, the desired output will be replaced from QL by QH, because now maintaining this body at temperature TH or rejecting heat QH to this body is our desired effect. So desired effect is QH and required work is W net. And similarly, if I write the relation for W net, you can see easily W net entering, QL entering, and QH is going out of the system. So this QH will be equal to W plus QL. And so W is equal to QH minus QL. So if I replace this W by QH minus QL, I will get this relation. Okay. Now you have a small task to do. Use this relation COP of heat pump. Use this relation COP of refrigerator and prove that COP of heat pump is equal to COP of refrigerator plus 1. You have got 5 minutes to do this. Take out notebook, pen, and prove that COP of heat pump is equal to COP of refrigerator plus 1. Okay, before that, I don't know what time has left out. Why meeting doesn't got ended after 40 minutes? We are continuing still 10:30, right, Pradeep?
Yes, sir.
So meeting doesn't ended, surprisingly. Okay, that is good for us, so don't worry about that. Okay, so before deriving this one, let's take a look of this video. Okay, so derive this one. COP of heat pump is equal to COP of refrigerator plus 1, and post that picture either personally to WhatsApp, or you can post it here in a chat window also, because meeting is still on, so you can post it in a chat window also. Derive fast. I'm still waiting. So derive it and post the picture to me, either in a chat window or through WhatsApp. Pratik, can you prove it or do I need to explain?
Explain, sir.
Okay. Let me write over here. Okay. So the relation that we need to prove is COP
Conversing
of
valve heat pump. I'll show you a simple
COP of heat pump is equal to COP of refrigerator plus 1, that we need to prove. So what is the relation for COP of heat pump? It is, I will write over here, QH, that is desired effect, by QH minus QL, right, is equal to, what is COP of refrigerator? Only desired effect will be changed. Instead of QH, it will be QL. QL by QH minus QL, denominator will remain same, plus 1. Okay. Now let's multiply this one with this one. So it will become QL. Is it visible whatever I am writing, Pratik?
Yes, sir.
Because I am writing it on picture also. Okay. So QL as it is plus QH minus QL as it is. This is QH minus QL. So I will multiply this QH minus QL with this 1. Divide by QH minus QL, the denominator as it is. So this is plus QL, this is minus QL. Those QL will get cancelled. And what remains in the numerator? This plus QH by QH minus QL. And what is there in on the right left hand side? It's already QH by QH minus QL. Now if you observe left hand side with right hand side, both are same. So we have proven that COP of heat pump is equal to COP of refrigerator plus 1. Or in other words, in exam they can ask to prove that COP of heat pump is greater than COP of refrigerator by unity. So if say COP of refrigerator is 0.75, then COP of heat pump operating between same temperature source and sink, it will be 1.75. Is that clear to everyone? Pratik?
Yes, sir.
Okay, so now I'll end the session. We will stop over here and we'll be beginning with the remaining part in the next session. So these are the some additional diagrams that you can use. Instead, if you find this one little bit complicated one, you can use this one for heat pump and you can use this for refrigerator also. Okay, so that's the only concern. Okay, so before coming for the next session, there is one question for you to think about. The question is, if you keep the refrigerator door open, can you cool your house or room in which that refrigerator has been placed? म्हणजे आपण जर आपल्या ज्या रूम मध्ये रेफ्रिजरेटर ठेवलेला आहे त्याचा दरवाजा उघडा सोडून दिला तर आपण त्या पूर्ण रूमचं टेम्परेचर कमी करू शकतो का? That is the question that you are expected to answer in the next session. Okay, so I'll end this session over here. Before that, I'm announcing it. I have announced it many times in the past, but I'm announcing it again. Visit the Google Classroom and attempt all the quizzes assigned to you. Yesterday or day before yesterday, I have assigned 8th quiz, and many of you have not attempted many quizzes. Okay, so it is a request to all of you to visit the Google Classroom and attempt the quiz. That is going to be considered while assigning internal marks to you. If you don't want to score good internal marks, then it is fine, but if you want to have those marks which are in hand, and that is going to help in scoring in that subject. So losing that marks is not expected from you, or that is not desirable also. So visit Google Classroom and attempt all the assigned quizzes. Okay, so I will end this meeting now. If you still have any queries, you can contact me through WhatsApp, text, or personal calling also. Okay, thank you so much. I will end this meeting now.